Good day everyone, I am Ranyag Katangkay. At this point, we are down to our last topics, periodicity and chemical bonding. In this lecture, we will discuss the following. Under periodicity are periodic table and periodic properties. For chemical bonding, we will discuss Lewis dot symbol, octet rule, ionic bonding, and so on. For the periodicity, let's start with periodic table. I hope all of you are familiar with the periodic table. This is from IUPAC. For this lecture, we will focus on the representative elements only. Representative elements are those elements from group 1A to 7A or based on the IUPAC grouping, group 1 to 13 to 17. We will discuss each of these groups individually. Let's start with group 1. Group 1 is called the group of alkali metals. All of these elements are metals except for hydrogen because hydrogen is a non-metal. Group 2 called alkaline earth metals. These elements are all metals from beryllium to radium. Group 13, the boron group, it houses boron. Boron is a metalloid. The rest are metals from aluminum to nihonium. Group 14, the carbon group, it houses carbon, a nonmetal. It houses two metalloids, silicon and germanium, and three metals, tin, lead, and flerobium. Group 15, called pnictogens. Under this group, we have an equal amount of nonmetals, metalloids, and metals. Nonmetals include nitrogen and phosphorus, metalloids arsenic and antimony, metals are bismuth and moscovium. Group 16, called chalcogens, it houses three nonmetals, oxygen, sulfur, and selenium, a metalloid, and two metals. Lastly, group 17, called halogen group, it includes fluorine, chlorine, bromine, and iodine. These are nonmetals, and astatine, a metalloid. Now, for the case of tennessine, I haven't included the character of tennessine because based on other sources, scientists aren't sure back then about the character of tennessine. But it is assumed that to behave like a metal. But recent references suggests that tennessine also behave like a metalloid. Again, group 1, 2, 13, 14, 15, 16, 17 are under the representative elements. Let us now talk about the periodic properties. We have the following. We will discuss their definitions and their general trend. So starting with the nuclear charge, effective nuclear charge is the net positive charge experienced by valence electrons. The trend increases from left to right and bottom to top. Please take note that this trend and all the other trends that we will discuss in this lecture will most likely be applicable to representative elements only, because there are a lot of variations within the other groups of the periodic table. So the general trend looks like this. The effective nuclear charge increases from left to right and from bottom to top. Next is the atomic radius. This is the total distance from the nucleus of an atom to the outermost orbital of its electron. Now for diatomic molecules, diatomic elements, it is half the distance between the nuclei of two adjacent atoms. So the trend increases from right to left and top to bottom. For diatomic molecules or other molecules or species that are bonded with other atoms, radius is pertained as this distance from here to here. The general trend looks like this. Now the ionic radius is a little bit related to the atomic radius trend. But the ionic radius pertains to the radius of a cation or an anion. When an atom forms an anion, its radius increases, whereas when an atom forms a cation, its radius decreases. The trend is the same as the atomic radius, but here we need to make sure that we compare separately cations and anions. So the trend is here. These are metals except for hydrogen. The trend increases from right to left and top to bottom. The same is true for the nonmetals. Again, this trend must be applied separately. You compare a cation to another cation, or you compare an anion to another anion, and not a cation to an anion based on this trend. If you will compare that way, it's best if you do it using actual values to get an accurate result. Ionization energy. This is the minimum energy required to remove an electron from a gaseous atom in its ground state. Here we have what we call the first ionization energy, second, third, and so on. The first ionization energy is the energy required to remove the first electron. If we will remove another one, then the energy required is what we call the second ionization energy. The trend increases from left to right and top to bottom. So to hammer the point, let us look at the ionization energies of the first 20 elements. As you can see, the second ionization energy of helium is greater than the first. The same is true for the other elements, though there are exceptions. So the trend looks like this again, from left to right and from bottom to top. Electron affinity. This is the amount of energy released when an atom receives an electron. This is the opposite of ionization energy. The trend increases from left to right and bottom to top. So these are the affinities of the representative elements plus noble gases. The trend increases again from left to right and from bottom to top. Lastly, we have electronegativity. This is the ability of an atom to attract electrons toward itself in a chemical bond. We have different kinds of bonding, which we will discuss later. Basically, the element that has a greater electronegativity value will receive electrons. This is the trend, left to right, bottom to top. So to summarize, effective nuclear charge, ionization energy, electron affinity, and electronegativity have the same trend, increasing from left to right and bottom to top. For atomic radius and ionic radius, don't forget for ionic radius to compare only cations and only anions. These properties have the same trend, increasing from right to left and top to bottom. Let's have an example. Arrange iodine, phosphorus, sodium, sulfur, and strontium in the following. Let us first locate these elements in the periodic table. We have iodine, phosphorus, sodium, sulfur, and strontium. For letter A, we have to arrange these elements in increasing effective nuclear charge. So the trend is this. It is increasing from left to right and bottom to top. We can simplify this diagram and it will look like this. We will use this line as a guide to take into consideration the position in terms of grouping and period. So increasing effective nuclear charge, comparing sodium and strontium, sodium based on the trend will have a lesser effective nuclear charge than strontium because going going in this direction, we have an increasing effective nuclear charge. Now for phosphorus and sulfur, phosphorus will have a lesser effective nuclear charge than sulfur based on this trend. So last is the iodine. So our arrangement will be sodium, strontium, phosphorus, sulfur, and iodine. Now I want you to try these examples from B to E for you to practice. We will now proceed to chemical bonding.